Mixer is an active RF device which is essentially used to multiply two signals, to literally multiply two different signals, and in that process achieve what is called as a frequency translation. We are able to multiply two different signals, RF and local oscillator LO, and get what is called as an intermediate frequency. So this one, LO means local oscillator. That becomes the input for this mixer shown by this symbol here, and IF is the intermediate frequency. So how that essentially works is mathematically the RF signal is going to have a certain frequency at the carrier frequency fc, then omega c is 2 pi fc, having a certain amplitude that can change with time. If the signal is encoded in the amplitude, then this becomes the amplitude modulated signal with a carrier frequency of fc. The local oscillator frequency is something different than fc, and we call that LO. FLO is the local oscillator frequency corresponding to this signal. So if we were to multiply these two signals, RF and the local oscillator, the cosine signals, we notice that we would end up, if you were to do the trigonometric sum and difference formulas, we will end up getting two frequency components, one which is omega c minus omega LO, and the other one is omega c plus omega LO. So the omega c minus omega LO is what we call as the intermediate frequency, this being the lower, this one is the lower frequency component and this one is the higher frequency component. Omega c plus omega LO is obviously the higher frequency component. So in a receiver, it is this lower frequency component, intermediate frequency, that is then extracted out, that still has this amplitude information prior to the demodulation. Now, how to get this V1 of t times V2 of t? How do we multiply two signals V1 and V2 given V1 and V2 here? How do we multiply these two signals? The essential building block is any non-linear device with second order non-linearity can be used. So we have seen that a transistor has the second order non-linearity because it is a square law device, or it could be even a diode for that matter. One thing to notice, when we are multiplying these two signals, we do get a high frequency signal here. Essentially, the same principle of a mixer can be used for even a transmitter. The case of IF is for the receiver, but if you are looking at an application of a transmitter where you have a certain baseband signal and you have a certain local oscillator LO, but you want to translate the frequency to something high, maybe a carrier frequency omega c here, then you can use a mixer to multiply them so that the output is going to be, the output omega c is going to be, maybe if we call this the baseband signal, or IF for that matter, the intermediate frequency, then it's IF plus omega LO. So this is in the transmitter way, where we are interested at the high frequency component because we want to translate omega IF from low to a higher frequency omega c, whereas in a receiver application we would want to translate omega c to a smaller frequency of omega IF, and so we are choosing the lower, what is called as the lower side band. Now let's look into how a nonlinear device can be used to multiply two signals. Simplest nonlinear device that we can know is a diode. A diode is a nonlinear device. If we were to combine the RF signal and the local oscillator signal, let's say this is the receiver chain where the RF signal is picked up by the antenna and a low noise amplifier amplifies it. The RF signal and the local oscillator are combined together, let's say they are added together, and then fed into any device that is having a square law kind of behavior. For example, in this case, the output of this detector, being a diode, let's say, is of a nature of having second order nonlinearity. That means the output is a squared of the input voltage. Then now that we have added the RF signal and the local oscillator signal, we have added the RF signal and the local oscillator signal, we are going to square that up. The sum of these two, we're going to square that up, and that essentially leads to multiple frequency components of the output. Of course, the first component is the DC component that does not depend with frequency. We saw this even in the intermodulation products video. So intermodulation products, essentially the nonlinear device is going to create a bunch of frequencies at the output, but what we are interested is not in the DC component, nor in the higher order harmonics of 2 omega RF or 2 omega LO, but what we are interested is in this particular two frequency bands, which is RF plus LO and RF minus LO. So that operation, this particular term, is what essentially the mixer is able to do it for us. So this filter that subsequently goes in is able to extract, this filter is able to extract this frequency component while suppressing these two. So let's take a closer look in detail at the two side bands that we can get when we are mixing two signals. For example, now that we know that we combine the RF and the LO together and feed in as an input to any square law device, then let's say the omega RF is at a particular frequency and omega LO is at a certain other particular frequency, then the output is going to be, if we were to match the RF over here, aligning them together, this is going to be omega RF and this is going to be omega LO. We are going to get two frequencies. One is omega RF plus LO and the other one is omega RF minus LO. And the one with the higher frequency is what is usually called as the upper side band frequency of the mixer, upper side band of the mixer output, and the one with the lower frequency is called as the lower side band of the frequency output. Now something interesting happens when we are having a mixer in a receiver chain is that when this mixing process is leading to two different side bands, lower and upper side bands, there are chances that if there is an interference somewhere below, let's say in this example, if there was an intermediate frequency, some interference frequency here, let's say that as the image frequency, what we call as the image frequency, chances are that this image frequency is so far away from the local oscillator frequency, as long as that is equally distant as the RF signal is, which in this case is going to be the intermediate frequency omega IF, then the upper side band of the image frequency can technically overlap, or the lower side band of the RF frequency can overlap with the image frequency. In other words, let's draw this out here, is if you had a certain omega RF at a particular frequency, and then we have a local oscillator which is, let's say, omega LO, and when these two are mixed together, we see that one of the frequencies that we get is the intermediate frequency omega IF, which is omega RF minus omega LO. Essentially this RF spectrum is nicely captured here at a different frequency. The frequency translation is done for us. But what if we had another frequency component at the input along with the RF, and essentially this omega RF is going to be the difference between the omega RF minus omega LO. That is going to be the intermediate frequency. If we had a frequency, image frequency, that is what we call as the image frequency, that is at a certain location which is equally far, this omega IF, which is equally far but at a different frequency component lower than the local oscillator frequency, then the chances, then if there is such a frequency, then the output of the mixer is going to appear at the same exact omega IF, which in this case is going to be mapping to the same exact location of omega IF. In other words, this image frequency, this is going to be the image frequency omega IM. The output is going to be omega IM plus omega LO. The upper side band of the image frequency is overlapping with the lower side band of the RF frequency. the upper sideband of the image frequency is overlapping with the lower sideband of the RF frequency. So if we were to work out the math, we would see that the image frequency is essentially the RF frequency minus 2 times omega IF, this being the 2 times omega IF. Essentially the image is 2 times lower, and in other words, it's going to be 2 times the local oscillator minus the RF frequency. So we wouldn't want to have this at the output. This must not be there. We are going to faithfully recover only the RF signal at the output. So the best way to do that is to have a filter in the first place to essentially, now that we know where exactly the location of the image frequency is going to be, is to first filter this off so that no frequency components exist at the image frequency prior to this operation of mixing. And that is what we call as the image reject filter. Image reject filter, which essentially is placed before the mixing operation is done. We call that as the IM filter, so that the image frequencies don't appear to pollute or interfere on the process of translation at the output of the mixer.